Today we're going to be joined by Peter Bauckham. Peter is the platform lead at Quizlet, and the two of us are going to be talking about running open source databases on Google Cloud Platform. So a few goals for today. We'll take a look at what we view as some of the most popular open source databases in the market right now, and we'll look at how you go about running those databases on Google Cloud Platform. We'll take a look at what Google offers, what some of our partners offer with respect to managed services, and we'll look at how you can self-manage these databases. And then Peter will join on stage, and he'll talk about lessons learned by Quizlet with respect to running MySQL on Google Cloud Platform. Quizlet generally has a really impressive MySQL architecture, and I know I'm excited that he's here to share some of their learnings through I think some pain and certainly some success as well running MySQL on Google Cloud Platform. So before I jump in, let me just ask a question to all of you. By show of hands, how many developers do we have in the audience? Okay, so about a little more than half the room, maybe even 2/3. How many database administrators do we have in the room? A few. How many reluctant database administrators do we have in the room? And there's a few more. And how many managers do we have in the room? We got a handful. Okay, great. Well, I hope the presentation will have something for everyone, and indeed I think it will. So let's get started here. We'll take a look at popular databases, and we're going to start with the analyst view of the world. This is an analyst view of the database market as measured by revenue or by market share. The bars you see on this slide are not to scale. If you look leftmost, we have our database market at just over $35 billion, and we compare that to the open source database market and the NoSQL markets at 300 and change million. So if we actually represented those at scale or in relative scale, those would be like a pixel, and you wouldn't be able to pick up the numbers there. The take on this, at least from my perspective, is that the analysts are measuring a market in a very rational way. They're looking at dollars spent or money spent on databases, usually in the form of database licenses and also in support contracts and associated services. Historically, this has very much benefited commercial databases that often come with large license fees. I think the reports like this tend to understate the significance of open source databases in business. And this is starting to change now. This view of the world is starting to change in that cloud vendors like Google, some of our partners, other cloud vendors, are offering database services based on open source databases, and they're finding significant interest from customers, and that's generating revenue. So these bars are starting to change over time. I honestly think what we have here is kind of a massive shadow market where if you surveyed everyone running an open source database, you've got a very large number of users depending day to day on open source databases, and it's not reflected in these type of reports yet. Okay, with that in mind, we're talking about the smaller segments on this chart, our open source database charts. We, Google, have a very casual relationship with the company called DB Engines. DB Engines looks at signals, things like job postings, development activity, and a number of other signals to determine how popular, relatively, are databases one to another. What we're showing here is a list of databases. You can see rightmost column, we've highlighted databases, relational databases like MySQL and Postgres, for example, along with MariaDB. We've highlighted some of the NoSQL databases, Mongo and NewSQL databases, Cassandra, Redis, Elasticsearch, HBase, and what you see is kind of a relative popularity. Note that the y-axis here is in log scale. So you have MySQL at the top, kind of the most popular open source database, at least as measured by database engines. And you see some others that are growing in popularity over time. Now, given the log scale, you've got some things starting down on the y-axis at 2, while MySQL is above 1,000, so bear that in mind. But we've seen in the relational space very steady growth in terms of popularity for a database engine like PostgreSQL, and you can see a number of the others that I've highlighted here growing in popularity over time. What we'll look at as we go forward are these databases, what options Google has for you with respect to these databases in Google Cloud, what options our partners bring in terms of managed services, and how you can get started self-managing one of these databases. And what I'll note here is as a product manager for Cloud SQL, which is a managed database service, I certainly have a bias. I love managed database services. But I think what it comes down to in terms of selecting, do I self-manage a database, do I go to a managed database service, is really the trade-off between customization and that time and toil in management. When I think about looking at a database service versus self-managing, I think you all are aware of the trade-offs you're making day to day with your time. As developers, as DBAs, as managers, you are deciding, I'm going to customize this part of my technology stack, and I'm willing to spend the time to maintain that part of the stack. Other parts of the stack, you may say, I'd like to turn this over to someone else. And in doing so, I'm going to give up some of the customization I can get by managing it myself. I think that's the trade-off you look at. So as we go through these options, hopefully they simply illuminate some of the options you have with respect to these databases on Google Cloud. And then Peter will join on stage, and Peter will take you through their rationale, Quizlet's rationale for self-managing MySQL, and some of the experiences they've had on Google Cloud Platform. So let's start with MySQL and MariaDB, which some will call a MySQL clone, certainly a fork of MySQL. For the Google offered service here, Cloud SQL, our managed relational database service, has for years offered MySQL. Cloud SQL, we say, is compatibility, but more than compatibility, we are more than just a compatibility layer, I should say. We are offering standard MySQL databases, and Cloud SQL takes care of often mundane maintenance operations, things like patching the database, patching the underlying operating system, making replication feel easy, your click button. We monitor high availability, for example, and you're backed by Google's team with respect to high availability. So it goes beyond just the tooling to make sure that a database is up, and if it's not, that we're failing over. You're getting someone in the end looking at these systems 24/7 so that you don't have to. That's kind of the essence of the managed database service. What I will note about Cloud SQL is that it is not a DBA. The hope with Cloud SQL is that for developers, it offers you a chance to develop, to focus more on your development rather than on database management. For DBAs, I hope it allows DBAs who choose to use Cloud SQL a chance to do something a bit more higher value with their time than installing or provisioning a database or patching a database, for example. We have a partner in ClearDB offering managed services in this very space as well. And we note in our launcher platform, which is pre-built images or OS images that include an installation of MySQL or Percona or other MySQL relational databases. We have those options for you. So as you kind of move down this chart, you'll see this again and again as I go through these. We have Google's managed service, a partner's managed service, and options for you to quickly get started self-hosting these databases. Taking a look at Postgres, Cloud SQL, as of yesterday at this conference, announced support for the first time for PostgreSQL. It was a long-standing request, and we're very happy to be saying yes to that request now. So Cloud SQL for Postgres just went beta as of yesterday, is launching right now. We have ElephantDB, who is running a managed service as a partner. And you see in the launcher space here offerings from EnterpriseDB, a strong Postgres partner, from Avon, who is offering a managed service as well. And we have Bitnami images, which effectively package a Postgres installation into an image so you can quickly get started with Postgres. One thing to note on the DB Engines ranking here, you see the rise in Postgres over time. I think the momentum behind Postgres right now is really exciting. It has a long history of active development, and we're excited as Google now to have an offering in the managed space here. Taking a look at Cassandra and HBase, Google has a product called Bigtable, which I hope you've all heard of. It has an HBase API layer, so when we talk about HBase at Google, we refer to Bigtable as kind of our product in this space. In terms of managed service offerings, our partner Instacluster, has offerings around the Cassandra space. And then, of course, we have launcher images, both Cassandra proper as well as from DataStax to help get you started with Cassandra. And you can see kind of some interesting movement in the Cassandra and HBase rankings in the DB Engines chart to the right. Looking at MongoDB, Cloud Data Store is our offering in this space. Data Store is often paired with App Engine for those of you who are familiar with it, but Data Store is great when it comes to big scale, and especially document storage. Looking at managed service offerings, Mongo Labs has an offering, as well as Compose and MongoDB. In the launcher space, again, we have standard Mongo options and MongoDB with replication to help you get going rapidly with MongoDB on the Google Cloud Platform. And looking now at Redis, we've recently unveiled App Engine Memcache. I think you will continue to see us innovate in this space. We think in-memory databases are important and caching layers are important there. The managed service offerings we have are via partnerships with Redis Labs and again with Avon, and we've got some representation from Avon, I think, in the audience potentially today as well. Looking at our launcher space, we've got kind of classic Redis as one of our launcher applications. If you haven't been to Cloud Launcher, take a look. We see customers getting some value out of Launcher, even if just for simple things like testing. And then those images can certainly end up in production, but it's just a quick way to get started with some of these applications on Google Cloud. So I'm very happy to now be introducing Peter Bockham from Quizlet. Peter's the platform lead, and Quizlet is a heavy user of MySQL and generally a heavy user of the Google Cloud Platform. So Peter, I think, has a great story to tell and hopefully some lessons learned that you can all benefit from with respect to running MySQL on Google Cloud Platform. So please join me in welcoming Peter.
Thanks. Hey everybody, I'm Peter. I work on platform at Quizlet, and I'm really excited to be here today. I think to preface this, there's an implication if I'm standing up here that we've solved all these problems and we have this perfect, great infrastructure that never goes down, and I definitely don't feel that way. But I think the value in these talks is just for us to give you information about how we run our infrastructure, and hopefully my goal is you'll come away from this with just a few more ideas and some context on what we do, and hopefully that would help you if you're running something similar. So that's my goal here. I'm going to give you a bunch of information about our architecture, some decisions we've made, how we configure things, etc. And hopefully it'll be useful, and there's going to be questions at the end. If you don't get your question in, I'll be around as well just to chat about it if you're interested in doing that. So I'd like to start with just a brief introduction to Quizlet if you haven't heard of us. Quizlet is an ed tech company. We make a study tool that you plug your content into, and then it helps you practice and master that content. So we've had really strong adoption in high schools, colleges, things like that. It's really good for vocabulary, foreign language, etc. We have a web and mobile native apps, and some stats on us. We have about 25 million users a month, and on Quantcast, we're like a top 25 US website. So we've grown from something pretty small into something that's having a major impact on education. So this has been our growth curve over time. So we're really lucky to have strong organic growth. But the things I want to point out here is this is a challenging domain to run databases in. So you can see we're an education company. It's very, very seasonal. So no one studies over the summer, it turns out. It's pretty quiet. So we get this big drop-off in the summer, and then every year in August, September, we hit back to school when US students return to high schools, universities, and we get this big jump. So that's also where our growth hits. So summer is, we really focus on load testing, preparing for that rush, and effectively, we are preparing for a level of traffic that we've never really seen. So this is difficult. We get these big seasonal swings of traffic, and we need to manage and deal with this. It's really important that we stay up and stable. If we go down, this is what happens. This is a tweet of a classroom. All the students are holding iPads that say Quizlet is down on them, and actually the projector in the back says that as well. And so I put this up here just to empathize with the user a little bit and underline why we feel this is important to us and why we care about running this really stably and performantly, and avoiding this kind of situation, which is hard. It's hard to see when this happens, right? So that's why we're here. Like many applications, Quizlet started pretty simple. It was our founder, Andrew, wrote it to help himself study in high school. And when we started, it was pretty simple. It was just an application in a database, written in PHP, communicating with MySQL. And as we've grown, as we've hit that growth curve over the past 10 years, we've had to scale this up. We've had to re-architect and solve this scaling challenge. So what have we done? So this may be a pretty familiar list to a lot of you. You know, we've done the basic stuff. We've added indexes. We've optimized our queries. We've done things like eliminating joins. So our queries almost always hit a single table. We've moved to bigger hardware, so we've just scaled up vertically. And we started caching query results. I'm going to talk a little bit how we use Memcached. We've moved to partition tables. So we've taken a single table and we've used MySQL partitioning to split that into multiple individual files on disk. We've compressed table data. This helps with disk I/O. And probably our biggest scaling effort has been around taking tables and splitting them out into their own hardware. So this is just vertical sharding. So our biggest tables we run on separate instances. Once you do this, you have a more complex architecture, but you get much, much more scale. We've also, because we use replication, we've started running queries on replica sets. So these are the queries that don't necessarily need to be exactly consistent. So if you do a write, you need to do a read. They don't necessarily need to be completely up to date. But this is a really nice scaling strategy. And once you do this, you can then increase the number of replicas and scale this way. So this has been our strategy. As I said, I'm sure that some of you are probably familiar with this and have done similar things. And I want to talk a little bit about kind of the implications of this on our architecture and what this actually looks like to run on GCP. So here's our current architecture. This is just a very high-level diagram. We have the web app. It's talking to these pods of master replica pairs. We run the replicas so that we can swap between when we need to do maintenance, or if there's a production issue on the master, we're able to fail over and promote the replica to a master and run that way. The important part is the replica is always there, and it's always ready if we need to swap over. We run a separate replica for backups, and we snapshot this replica, and I'll explain a little bit more about that. As I mentioned before, we've taken tables and we've split them into their own hardware. So we've ended up with, we now run in production 8 of these like pods of master replica pairs. And in some of these pods, like in the middle here, we run multiple replicas. So we've scaled in that way. And then finally, we run this tier of caching. And this is the application communicates with this pool of Memcache machines. And this alleviates some of the load on MySQL. I'll talk a little bit more about that. So what does our workload look like? As I mentioned, we've split out into separate pods. We have about 3 terabytes of production data, and if you add in the indexes, that's another 2.2 terabytes. So I think of this as kind of a medium-sized workload. There's many MySQL workloads that are much, much larger than this, but this is basically the domain we've scaled into. During an average week, we peak around 28,000 queries per second, and that's kind of spread across all of our databases, across all of the replicas. And in total, we have about 40 billion rows, and that's across 100 tables. So, you know, whenever we add a feature or something like that, we often end up with an additional table, and so the app is communicating with about 100 tables in total. So this is the shape of the workload. And you know, there's a bunch of entities in there. That 40 billion rows, it's both the content, so the Quizlet, our content is term and definition pairs. That's what people are studying. But it's also some more analytical things. So we record every answer that anyone punches into Quizlet, and we can use this to help people study later on. So this is important data. And it's important that it's in the production database rather than just an analytical database, so we can use it in the application and help drive studying later on. So this is our traffic during an average week. I think this is pretty common with a lot of consumer-facing companies, but this is starting Saturday, so you can see not much studying on Saturday. Sunday night, we start seeing this hump, and then during the week, we see a bunch of traffic in the morning. This is when people are using Quizlet in school, in the classroom. And then we see another hump at night. And so this is when people are studying at night for the next day. So you'll notice that we don't see that evening hump on Friday night. So I think one question that I would have is, so why are you guys doing this? Why aren't you running Cloud SQL? It's the managed service. It would solve a lot of these problems. So my philosophy on this is you should use managed services whenever and wherever you can, and they have a huge, huge potential to save you time, save you money, save you operational costs, et cetera. We moved over to GCP a couple of years ago, And at the time, we needed larger machines than Cloud SQL offered, and we've kind of continued to scale up to larger machines. And so we're now running on 64-core VMs. We'd also had operational experience running MySQL on our previous cloud, and so we had a relationship with Percona, and we've tuned our databases specifically for our workload with Percona. So some of the configuration was specific to us, and we wanted to continue having control over those. We also had experience managing the replication and failover, and we like to control that because we know, where you are in the recovery step and what the replication is doing, and being able to handle that kind of promotion and that kind of thing. There's a maintenance cost there and complexity cost, but we wanted to be able to handle that ourselves. But as I said, we're very, very optimistic about hosted infrastructure, and we use it wherever we can. And we'll likely revisit how we run this stuff over time. So how have we configured this? What does this look like? So we run Percona MySQL 5.7. This is a recent Percona release. And as I said, we run a bunch of different machine sizes. So the smaller machines, the backup machines, are 8-core. They're the standard 8s. And this scales up to 64-core machines. So we're using the High-Mem 64 cores, which are about 400 gigs of memory. And those are where we need the most power, and we have the biggest database workloads. We're using the Google just vanilla PD SSD drives. So this is 25,000 IOPS. And so we've optimized our workload around kind of that ceiling and that number, and it's important to us. We're also using GTID-based replication. So the thing to know about that, if you're not familiar with that, GTID replication is a way of tracking the transactions that have been sent to a replica and then executed on a replica. And they're important because if you have two databases that have the same GTID executions, then you can be pretty sure that they have the same database state. So it's a really convenient way of managing this. And when we're swapping in replicas, we ensure that there's GTID consistency there. So I just wanted to call that out as an important piece of this. We've done a number of things to tune the workload, and the things that I want to highlight there are the biggest configuration changes we've made from a performance standpoint have been to tune the buffer pool sizes and optimize this, and tune the number of buffer pools. So buffer pools, as you may know, it's how MySQL is caching pages in memory. So it's a MySQL managed cache, and we tune this to be around 8% of the memory on these machines. When you're running machines with a number of cores, so 64 cores, you're going to end up with a number of worker threads, and the buffer pools are a shared resource. And so if you don't scale the number of buffer pools with the number of CPU cores, you end up with contention. So we found it very important for our performance to optimize the number of buffer pool instances. And the current number we use is two CPU cores to a buffer pool instance, though we may experiment more with that. So next I want to talk about how we access this from the app. So what does it look like on the ground when the Quizlet app actually talks to MySQL? So Quizlet was originally written in PHP. It's originally just a PHP MySQL application. I think a lot of apps start this way. PHP is not the favorite language of many people, and so what we've done is tried to optimize how we use it, improve how we use it, and the state we're in now is we're using HHVM, which is Facebook's PHP just-in-time compiler. It carries a number of advantages. We were able to significantly reduce our machine footprint. We cut our number of web servers by about half by switching to HHVM. And it also introduces a layer of type information. So if you're just running vanilla PHP, HHVM attempts to detect the types you're using and optimize based on that. We've also begun using a language called Hack, which is based on HHVM, and it carries a number of features, but at its simplest, it's like a typed PHP. So we've transitioned a lot of our code into Hack, and this has had a lot of benefits, and the application developers are pretty happy about this. So application running in HHVM, we're communicating with MySQL via HHVM PDO, which is an extension written in C++ that handles details of connections, queries, etc., and communicates directly with MySQL. So all of our queries are going through HHVM PDO. Finally, moving a layer up, we're running a custom ORM. So within our application, this big HHVM application. Queries are going through this ORM. As you can see, I've included a sample query at the bottom here. This is a Fluent interface we have for composing queries. You can do things like add query predicates, filters, etc. You can mark a query as read scalable, which means it's OK to send to the replica, and it doesn't need consistency. And then this is going to handle the actual composing the SQL query and sending the results back. So this is how we're actually forming the query, communicating back to the application. This is what our developers are interacting with. So I want to talk about caching for a second. This, I think, is an interesting piece of this puzzle because the caching gets a little tricky. I want to explain why. We run a pool of Memcache machines. I think this is a pretty standard architecture. We do consistent hashing, so each web node is communicating with each of the Memcache nodes. And we're hashing consistently, so each key from all the web nodes ends up on the same Memcache node. So we're basically utilizing Memcached as a cache for MySQL. The advantage here is we reduce query load, so we're sending fewer queries to MySQL. But we're also, because we're storing this in cache, we are freeing up a lot of the MySQL cache for other queries. So things that would have been going in the buffer pool, increasing buffer pool turnover, et cetera, are instead just going to Memcached. So this is great, but this gets tricky. Remember, there's really only one source of truth for our data. So MySQL is the source of truth for our data. The whole thing rests on MySQL. It's our transactional relational database. And fundamentally, if we do a transaction, if it fails to write to Memcached, the transaction still succeeds, but Memcached is out of sync. So this is particularly important because we're using Memcache as a model cache. So literally, our models in MySQL, or our models in the application, we're serializing those and we're storing those in Memcache. And so when those get out of sync, you can see, you immediately have inconsistency in the application. So we mitigate this partially by setting a TTL on everything we write to Memcached. So effectively, when this happens, there's a limit on the inconsistency you could see. But it's important to keep this in mind. There's the possibility of inconsistency. For example, if there's a network disruption, you'd see this. And certain things you don't want in this framework. So for example, queries around billing, right? You don't want that to happen. It's really, really critical. So we utilize caching, I think, pragmatically. We think it's really beneficial to reduce the load on MySQL, but it's really important to keep this in mind when we're using it. And we've played around a lot with this about where do we set the TTL, where do we bust the cache, et cetera. There's another layer of complexity here that if you rebalance the cache buckets and then you rebalance again, you also have the chance of stale data. So we've spent a lot of time thinking about this, about how we manage the cache pool, and just attempting to be thoughtful and avoid this situation. What I'm getting at is basically, if a Memcache node drops, what do? One perspective may be you rebalance your cache, but if this is flapping, you can end up with a lot of stale data. So we actually never rebalance the cache when we use it. So next I want to talk about our database failover infrastructure. What I mean by this is we frequently need to fail over from a master to a replica and promote the replica to the new master. This is tricky because fundamentally you need to ensure data consistency, and you want to do this while you're running the application. You want to reduce downtime. You want to reduce the problems you're seeing. So here's how we handle this. We're doing service discovery with console, and the way this works is console holds the master and the replica, holds the IPs, and then we're templating files from console. So this means we're able to change a value in console, and then this templates the value into config files on all of our application servers. And this happens really, really quickly. So that's how we do the service discovery, but the application still needs to be aware of which is the master when, and we need to ensure that there's consistency when we do this failover. This is a little bit tricky. So here's our process for this. we kick off this process. We pick a replica. We know we want to swap over to this replica. We're going to the master. And the first step is to snapshot that replica. So this will come in useful later on when we restart replication. So we snapshot the replica. We then lock writes on this whole system. So on the database we're switching, we stop doing writes. And this is because we need to wait for the replica to catch up. We need to wait for the failover. So we lock writes. This is critical because this has a major impact on the app. The database that you're doing this failover on, you're then effectively not serving that to users. So this is a major impact on how the application is running. So we lock writes, and then we wait for the replication to catch up on the new master. We're waiting. In practice, our replicas are often within a second of the master in terms of transactions. But we want to be really extra sure that they're caught up, because if you don't wait for replication to catch up, you're effectively leaving writes behind when you swap to the new master. So we wait for replication to come up. We promote the replica to the new master. So this is where console comes in. This is where we change the service discovery. We're templating the files on all the application servers, and then they know that, okay, this is now the master. We then unlock this database. So this is kind of the point of no return, right? This means we are both writing to the new master and reading from it. And so this is the point of no return because you then can't go back to the previous master without losing writes. So this is a critical piece of this. So we've unlocked, the application comes back, we're reading and writing, and then the next step we need to do is to restart replication the other way. So in other words, the old master now needs to replicate from the new master. This isn't strictly necessary, but what we do to avoid replication problems is that we then restore the snapshot from the old replica, put that on the new replica, so we ensure there's complete consistency, the GTIDs match exactly, and then we restart replication. So now we're running fine, we're running smoothly, we're back in action. This actually gets even more complex with multi-replica pools. So as you can imagine, you then need to pick one of the replicas to fail over to, and any other replicas then need to be aware of this process and point to the new one. So as I mentioned before, there's a lot of complexity in managing this. We have experience with this, and we have scripting around this, but there's complexity. The scripting is difficult to test because to test it really thoroughly, you need a very robust staging or integration testing environment. And yeah, so the point I'd like to make is just that there's complexity. We manage it because we like having control of it. We like knowing exactly the characteristics of when the failover is happening, and being able to fix it if something breaks. But there's cost to it. So next I want to talk about something that's super important to us. This is backups. So we're replicating data to another replica, which is smaller. And the purpose of this machine is just to keep up with the write load and keep a state with the master. So in other words, fall closely behind the master. We're not reading from this node at all. This is one of my favorite parts of GCP. This is one of the things we liked most when we were evaluating GCP as a potential platform. The GCP snapshots are very, very quick. So even multi-terabyte SSD drives, we can snapshot those like literally in a matter of minutes. This is pretty significant because what it means is you can get a full copy of a disk, consistent. It's really, really quick, and it's fast enough that we're able to do this once an hour. So if we were to lose the running instances we have, the most data that we would lose in that scenario is an hour's worth of data. So this is pretty nice. We press the snapshot button, it goes, it saves, and we have this guarantee. So there's some other things we want to do in this infrastructure. So one is we want to test these backups. We want to make sure that they're consistent, they're sane. If we need them, we can bring them back in. And we also want to store some copies of this elsewhere. So we want to store copies in the event that we would lose access to GCE. What if we lost access to our entire GCP account, et cetera? We want to solve that problem as well. So this is what our architecture looks like. As I mentioned, we have this backup replica. This has an SSD that we're snapshotting. And then we do a couple things with this drive. We take the snapshot, we turn it into a disk, and then we mount it on 2 other machines. So first is a backup tester. All this machine does is it looks for an untested backup. It brings it in, it mounts the drive, and it does the MySQL recovery. So once the MySQL recovery is done, you can run queries on this. And we just run pretty simple queries. So we're making sure the data is like sane, the tables are as large as we expect, we're seeing recent timestamps in the tables, etc. The worst case scenario here is you try to do a backup and you realize your backups are broken. We do testing to ensure you don't see that, right? We also have an archiver. And what this is doing is it's mounting the drive, it's tarballing up just the raw binary MySQL files, and then it's shipping those off into cloud storage. So we're shipping it to GCS, and then we're also shipping it to S3 to ensure we have a backup that's just outside of our GCP account domain. So, this is important to us because we want to make sure that if there's a disaster, we can recover, our backups are sane, coherent, we have copies elsewhere, etc. So we've put some time and thought into this. I also want to talk about data warehousing. So this is great. We've solved backups, we've solved replication and failover, etc. But our data analysts, they want this data. MySQL is not. There's a class of queries that MySQL is really not intended for, right? Analytical queries, queries over your entire data set, large scans, etc. So at the scale we're talking about of a database of several terabytes, there's a lot of queries that a scan over the entire database is going to take hours, right? So we use BigQuery as our data warehouse. We really like BigQuery, and we push both production data, so the MySQL data into BigQuery, but also event data. We're streaming there. And so to join these 2 data sets, we need to do this. We need to do this copy. So how do we do this? This is a diagram of this process. Basically, we've written a Go client, and all this client does is it's executed on a cron. It's scanning through the entire backup machine, and it's streaming this into a GCS file. So what we end up with is a group of files sitting in GCS. I believe they're JSON format, and it's an entire copy of our database. Once it's in GCS, it becomes easy, right? You press a button, and you're able to import it into BigQuery, and BigQuery actually handles the table swapping of. In other words, we have a new copy of the data, we're putting it on BigQuery, and then we need to swap it in for the old table. So BigQuery is handling that for us. So remember, this is a totally separate system, and this is executing on a cron. So this is not up to date, up to the minute. It depends on the table size, but we run this for some tables every day and for some tables every week. So they're separate systems, and there is a delay there. But it's a big win because you're then able to process the MySQL data in BigQuery, and you're able to join that against our event data, which is also sitting in BigQuery. So we really like this. We really like this architecture. We really like BigQuery, and it's been really powerful for us. So as I mentioned, this is kind of unfinished, and there's a lot of improvements. We're always iterating on this. And I just kind of want to call out something that we internally at Quizlet think about and want to improve. So one is we want to improve our scripting around failover. There's a lot of complexity here, but quicker failover is better. There are a few things that we want to do to increase the speed with which we can do this. And the other thing that we see is that recovery sometimes involves manual steps. So if replication is off, if the GTIDs are off, etc., we've seen cases like that. That sometimes involves the developer actually going and looking at those. And those we'd like to narrow down on and eliminate. Another thing that we see is the larger GCE instances. Live migration is not totally transparent for systems that are running really, really heavy transactions. And the effect of this is effectively your machine just kind of drops for a second. So you'll see there'll basically be a live migration blackout. The machine will disappear for a few seconds, then it'll come back. So this is pretty tricky. You want to be able to trust the VM. We mitigate this by we watch for these. So there's a notifier you can watch that'll tell you when the live migration is coming. But fundamentally, you need to avoid single points of failure, and you want to avoid relying too much on a single machine. As I said, the bigger machines are more susceptible to this, so the smaller machines you can run, the better in a lot of cases. A big problem with our architecture is we haven't horizontally scaled yet. So we're not doing sharding of a single table across multiple databases. And we've done this basically to be pragmatic. There's a huge amount of complexity that comes with managing sharding yourself. There's a lot of solutions in this space as well. And effectively, we've been able to punt this problem and shard vertically rather than horizontally. But it represents a pretty fundamental limitation on this architecture. But one of the things we're looking at is what other technology we can leverage. As you saw, we have a really strong growth rate, and so our architecture is going to continue to change, and we're going to have to adapt to the requests from users coming in. So we've been experimenting with Cloud Spanner as a replacement for MySQL in certain places, and an option for continuing to scale this up. And so actually, we did a talk yesterday about what we learned about Cloud Spanner as a replacement for some of this architecture. And we have a blog post about this as well. So it's also targeted at kind of if you're running a MySQL architecture and you are figuring out what the next step of that looks like, it's intended for you. So that's what I have. I hope this was useful and helpful. And I think we're going to take questions. But if you don't get your question, I'll be around as well and happy to chat more about this stuff.